Hello dear friends and students, welcome to the next video in DC machines. So in the previous video we have introduced about what is a machine, what does a machine means, and what else you call a machine, an electric machine, rotating electrical machine. It's also called as electromechanical energy conversion device. Similarly, we have seen about a transformer. Transformer is an electromagnetic device. It's a static device. It's not a rotating device. Misconception was there, and we have cleared that. And regarding why do we use magnetic field as a coupling medium between input and output stages, why not an electric field? So now we will just start entering into certain basic concepts before actually studying DC machines. Okay, so I was telling earlier, when you are talking about machine, okay, a machine can be either a motor or generator. Okay, a machine, okay, can be a generator or motor. Similarly, DC machines are also two types: DC generators or DC motors. So either could be possible. So generator actually produces electricity. So output is electricity. Output of motor is a motor. So electricity. So what does it actually produce in electricity? So any generator, when it produces electrical output, it actually what produces is voltage is what it produces. Okay, because voltage is nothing but the electromotive force. This is when voltage comes into existence, you get current and power and all the other quantities come into existence. The starting point is voltage. So any generator, okay, any generator is nothing but a voltage source. Okay, any generator is a voltage source. Voltage is nothing but EMF. Okay, voltage is nothing but EMF. So it's a source of EMF or source of voltage generator. So we have to study how a generator will produce this EMF. Okay, so we have to talk about EMF production. So before that, we have to talk about a great scientist called Faraday, who has given his laws named as Faraday's laws. Okay, so Faraday's laws are important now. So Faraday's laws of electromagnetic induction. Faraday's laws of electromagnetic induction. He has given these laws in the year 1831. However, he has given in 1831 these laws, but to actually commercialize a DC machine based on these laws, a DC generator, it took nearly 55 years. It was in 1880s when actually Edison, okay, Thomas Alva Edison, when he started constructing a DC generator and started building power systems in the 1880s in New York City. So these all the machines are based on laws of electromagnetic induction, Faraday's laws of electromagnetic induction. So these Faraday's laws of electromagnetic induction are two. So we will talk about the first law. Okay, first law of Faraday's. Okay, the first law states how to produce an EMF. Okay, so we will start quickly by stating the law. Okay, whenever a conductor cuts a magnetic flux, okay, and EMF is induced in it. Okay, whenever a conductor cuts magnetic flux, an EMF is induced in it. So what is the basic idea behind this? So let us start talking a little practical. Okay, so he says that a conductor cutting a magnetic field, an EMF is induced in it. So first we will list out the requirements. Okay, requirements to produce EMF. Okay, requirements to produce EMF. So according to this principle, so by seeing this principle, we can say that we need a conductor and we need a magnetic flux and we need a cutting action. Okay, so I can say we need a conductor next thing is I need a magnetic flux and we need a cutting action, right? So to cut, okay, to cut one object by other object, you have to move. There should be some relative motion between them. I can say relative motion is required. So these are the three requirements to produce EMF as per Faraday. So a conductor, a magnetic flux, a relative motion. Now to provide this cutting action or nothing but a relative motion, there are two ways to do this. Okay, one way is called as space variation. The other way is called time variation. Okay, space variation and time variation. Now we will talk about space variation. Space variation means in this space, okay, physically. So whenever a conductor cuts a magnetic flux, say here this is a magnet, okay, north pole, and there is a south pole like this here. Okay, flux is traveling in this way like this. Now I am placing a conductor in this magnetic flux, this red color conductor, and I will move this. Okay, now in a magnetic flux I am moving my conductor. So when I'm actually moving my conductor in space physically, the conductor is cutting the flux, what we say. But what is actually happening? What actually happening is when the conductor is rotating in that magnetic flux, it is occupying different positions in that field. Okay, so sometimes it is closer to the pole, sometimes it is away from the pole. So what is actually happening when it is occupying different positions? The magnetic flux linking to the conductor. Magnetic flux linking to the conductor means, in simpler terms, you can say magnetic flux touching to the conductor, right? So the magnetic flux touching to the conductor is changing at different positions. So that is what we mean by cutting action. By cutting action, I mean that the magnetic flux linking to the conductor must change. Okay, so when you are actually rotating physically in the space, the flux linking to the conductor is changing. Okay, so this is called as a space variation. So EMF produced due to space variation is called as dynamically induced EMF. Okay, this is called as dynamically induced EMF because dynamically means because there is some motion associated. So there is a motion associated means it's a mechanical device. So all generators, okay, dynamically induced EMF is found in all generators. Okay, in all the generators, be it AC generator or DC generator, EMF induced is dynamically. So all generators. Okay, all generators have dynamically induced EMF. Now we will talk about time variation. So what is time variation? Means with respect to time, there is some variation that is from seeing those terms. So what is actually happening? So in dynamically induced EMF, I placed a conductor between flux, in flux. And you see this flux is a steady flux, okay? Steady flux in the sense whose magnitude or its polarity does not change. Its direction of flux does not change. So that is a steady flux. So for dynamically induced EMF, the magnetic flux must be provided by a DC source, okay? DC excitation. Because magnets are two types. We know magnets are two types, permanent and artificial. Permanent and artificial magnets. Okay, artificial magnets are nothing but electromagnets. So now, how do we electromagnetize a magnet? Okay, how to make an electric magnet, electromagnet? Suppose it's a well-known aspect or a well-known concept. Suppose say there is a bar like this, and on this bar let us make a winding, a coil winding. Okay, a winding in this way on this bar. Okay, when you make a winding around a magnetic material like this, and you just connect it to some source. Okay, to some source, and you pass some current through this, then it will become a magnet. It will have its own north pole and south pole based on the direction of current flowing, okay, which is given by Ampere's right hand rule. So right hand rule here would be, if you see the direction of thumb will give you the direction of north pole, and remaining finger specify the direction of current. Now you see here, suppose direction of current is like this. Now current is going like this. Okay, current direction is towards the top, it's going from the back and it's coming up like this. So okay, this is the direction of current. Okay, this is the direction of current in this given case. Okay, so current is going towards the top, current going towards the top. Okay, now so you see my fingers are going towards the top, therefore my thumb should indicate the direction of north pole. So this way, okay, this way. So for me it is like this, okay, toward this way. So this is the north pole and this is the south pole. So I'm doing with the right hand, you please do it for yourself. Okay, yeah. So this is how you electromagnetize. So to electromagnetize we need a source, some electric source. So these sources are two types, AC source and a DC source. You know, DC source means constant source, so therefore flux produced is also a constant. So it's called as a constant field excitation. But whereas AC is not a constant current, okay, it varies with respect to time. So if you are producing a flux with the AC source, the flux also follows the same thing, it varies with respect to time. So that is what we are actually referring here. So in time variation you have a AC source for excitation, whereas in the space variation you use DC excitation. In time variation you require a AC excitation. And another important property is, to get dynamically induced EMF you require DC excitation only, not AC excitation. Dynamically induced EMF is possible only with DC excitation. Okay, now this is what we require, AC excitation now for time variation based EMF. Okay, so what is happening when time variation is happening? So I told we require conductor, magnetic flux and relative motion. Now this magnetic flux is produced by a AC source. AC source means always changing. Suppose you place a conductor in a magnetic field, okay, but the magnetic field is AC, it is changing with respect to time. So without actually having to move the conductor in the space, the flux linking to the conductor is changing, because naturally due to the nature of the flux, which is alternating nature. So here you don't need any movement to change the flux linkages. So automatically you are getting the flux linkages because of the behavior of the flux, because it is excited by an AC source. So you will get an EMF induced. So since there is no actually any motion involved, this kind of EMF is called as statically induced EMF. Statically induced EMF. Okay. So for statically induced EMF, you need AC excitation. So each of this is an important observation or important bit objective for any exam. Okay, any competitive exams, GATE, IES or whatever. Okay, for space variation, we get dynamically induced EMF. To get dynamically induced EMF, we need DC excitation. And all generators will have dynamically induced EMF, because generator is a device which converts mechanical energy into electrical energy. Dynamically means EMF is induced mechanically. There is some mechanical motion, whereas statically You don't find it in a generator, because generator itself is an electromechanical device. There is some motion, whereas statically induced EMF is found in a device which is static. So we have seen in the first video, what was that device? Transformer. So transformer has a statically induced EMF. Transformer has statically induced EMF. So now we understood two types of EMF, dynamically induced EMF and statically induced EMF, and their origins. Now let's perform some mathematical analysis on these concepts of dynamically induced EMF and statically induced EMF.